Okay, I want you to visualize something with me. A scene we have all, I think, seen 1,000 times. Just imagine a kitchen table. Maybe it's a bit wobbly, one leg is a little shorter than the others. And sitting right there on the edge is a cup. Let's say it's your favorite mug.
Oh, no.
Yeah, your favorite one filled to the brim with water. It's just teetering there.
I can already feel the anxiety building up. I know exactly where this is going.
Of course you do, because we all know how this story ends. Someone bumps the table, the cat jumps up, gravity does its thing, the cup tips over, it falls, and then
Smash.
smash, the water splashes all across the floorboards, soaking into the cracks. The ceramic just shatters into 100 jagged little pieces that skitter under the fridge. It is a complete, irreversible mess.
It is a tragedy for the mug, for sure. But for a physicist, that specific moment, that crash, is one of the most interesting things that can possibly happen in the entire universe.
Right. Because I want you to imagine that you filmed that whole event. You've got a high-speed camera, 4K resolution. You're capturing every single droplet flying through the air. If you play that film forward on your TV, it looks totally normal. Cup falls, cup breaks.
Yeah.
It's mundane.
Yeah, happens every day.
But now, and this is the image I want to burn into your brain for this entire deep dive, imagine hitting the reverse button. Imagine playing that film backward.
And this is where reality completely breaks down. This is where things get, spooky.
Exactly. If you run the film backward, what do you see? You see this puddle of water suddenly gathering itself up off the floor, defying gravity, rushing back into a central point. You see the shards of ceramic just jumping off the linoleum, fusing together in midair to form a perfect, seamless cup, capturing the water inside it, and then it softly floats upward to land gently on the table.
And if you saw that happening in real life, not on a screen, but right there in front of you, you wouldn't just think it was some kind of magic trick. You'd think you were hallucinating. You'd think the universe had just snapped.
Because that never happens. Not ever. In the entire history of the universe, as far as we know, we have never seen a broken cup reassemble itself. And that intuition, that bone-deep feeling that this sequence can happen, but that sequence cannot, is the mystery we are unpacking today. We are talking about the arrow of time.
It's the reason we remember the past, but not the future. It's the reason the universe is getting bigger and not smaller. And it's the reason why you can turn an egg into an omelet, but you can never, ever turn an omelet back into an egg.
We're diving deep into the work of the late, great Stephen Hawking today. We're specifically looking at his analysis of time and entropy and the origins of the universe. And I have to say, going through this research, it's not just about physics. It feels almost philosophical.
It really does.
It connects the shattering of a coffee cup to the expansion of the entire cosmos in a way that is just startlingly consistent.
It is so elegant, and it's deeper than just time moves forward. Hawking's mission here was to explain why time has a direction at all. Why does it have an arrow? Because, as we're going to see, the fundamental laws of physics, the actual equations that run the universe, they don't seem to care about time.
They don't have an arrow built into them.
Not at all.
Which is a wild paradox, and we're going to spend a lot of time on that. We're also going to cover a moment where Stephen Hawking, one of the greatest minds in human history, admitted he was completely wrong about how time works. He effectively thought time could run backwards, just like that film of the cup, and then had to publicly correct himself.
And that is such a fascinating story of scientific integrity, often called the great reversal mistake. And it tells us so much about how science actually happens. It's not just, downloading truth from the universe. It's making mistakes and then fixing them.
I love that. So we've got broken cups, we've got the Big Bang, we've got memory, and we've got Stephen Hawking admitting a mistake. It is a lot to cover. Let's get into it.
Let's dive in.
Okay, so I want to start with the concept of time itself, because I think for most of us, just, walking around, living our lives, we view time as this steady drumbeat, tick-tock, tick-tock.
Right.
It's the background noise of the universe. It flows from the past to the future, and it feels absolute, like my now is the same as your now. If I clap my hands, everyone in the universe agrees that I clap them at this one specific moment.
And that was the Newtonian view for centuries. Isaac Newton and really almost everyone up until the early 20th century believed in absolute time.
Right.
The idea was that time was this separate rail that the universe just ran along. You could put a label, a time label, on every single event in the universe. If a star exploded a million light years away and you clapped your hands here on Earth, there was a definite objective answer to which happened first, or if they happened at the same time.
It's sort of the God's eye view of the universe, a master clock ticking somewhere out there in the cosmos.
Right. But then Einstein completely crashed the party with general relativity, and he proved that absolute time is an illusion. It simply doesn't exist.
And this is the time is relative concept, which is super famous, but I feel like we often gloss over what it actually means for our daily reality.
Well, what we realized is that time is personal. It's relative to the observer. If you're moving extremely fast, like close to the speed of light, your clock actually ticks slower than the clock of someone who's standing still.
Okay.
And gravity does it too. Time moves slower near a massive object like a black hole compared to how it moves in empty space.
Yeah.
So there is no unique absolute time that everyone can agree on. Your now, my now don't have to match up.
So if I'm on a spaceship zooming away and you're here on Earth, our watches are literally drifting apart from each other.
Exactly. They're ticking at different rates.
Okay, so time is squishy. It stretches and squeezes depending on how fast you're going or where you are. But here is what confuses me, and I think this is where the real mystery starts to kick in. Even if my clock is ticking slower than yours, because I'm zooming around in space, we both still agree on the order of events, right?
Yes.
We both agree that the cup was whole before it was broken. We both agree that yesterday happened before today.
Yes. And that's the core mystery.
Yeah.
Even though time is relative, the direction of time feels absolute. We never see things happening in the wrong order. Why? Because when you look at the fundamental laws of science, the equations that describe how atoms bounce off each other, how gravity works for orbits, how electricity flows, those laws generally do not distinguish between the past and the future.
Unpack that for me a little bit. You're saying the math itself doesn't care which way the clock is running.
Precisely. If I show you a video of two billiard balls hitting each other on a pool table, and I play it forward, they bounce off. If I play it backward, they just bounce off.
Yeah.
The physics looks perfectly fine in both directions.
Right.
If you wrote down the equations for that collision, there is nothing in the math that says t for time has to be a positive number. You can make t negative, and the equation still balances perfectly.
So at the micro level, the level of individual atoms, there really is no arrow of time.
Not in the way we experience it. And to understand why, we have to look at these things in physics called symmetries. There are three big ones, C, P, and T.
C, P, and T. Okay, that sounds like a law firm or a vintage rock band. Let's break them down because this seems technical, but it feels really crucial for the argument.
It is. It's the whole foundation. Think of these as little tests we can run on the universe to see if the laws hold up under different conditions. The first one is C. C stands for charge.
Charge.
That means swapping particles for their antiparticles.
So swapping all the matter in the universe for antimatter.
Exactly. If you take a universe full of protons and electrons, and you magically swap them all for antiprotons and positrons, the interactions, the way they orbit each other, the way they bounce, should effectively be the same. The laws of physics should hold.
Okay, so C is the antimatter swap test. What's P?
P stands for parity. That's essentially taking a mirror image of the entire universe. Left becomes right, and right becomes left.
Like looking at the whole cosmos in a giant bathroom mirror.
Precisely. And for a long time, physicists thought that if you ran the universe in a mirror, all the laws would be completely identical. But then in the 1950s, they discovered that wasn't quite true. The weak nuclear force, that's the force that causes radioactive decay, it actually behaves differently in a mirror image. It has a handedness to it.
That is so bizarre. It's like finding out a vampire really does have no reflection. So P symmetry was broken.
In a way, yes, on its own. So physicists said, okay, well, maybe P alone is broken, but surely if we combine them, if we swap matter for antimatter and look at it in a mirror, then the laws must hold. And generally, yes, the combination of C and P together is respected by the laws of physics.
Okay, so C is antimatter, P is a mirror. That leaves T.
And T is time. T means reversing the direction of motion of all particles in the universe. It's exactly like running that film with a broken cup backward.
So the big question is, do the laws of the universe hold up if we do these swaps?
Well, here's the logic puzzle. There's a fundamental theorem in physics called the CPT theorem. And it says that any reasonable theory of physics, anything that actually describes our universe, must be unchanged by the combination of all three. C, P, and T all together.
So if you swap matter for antimatter, look at it in a mirror, and run time backward, the laws absolutely must hold.
Exactly. The math demands it. Now, since we know that the laws governing matter are generally unchanged by C and P combined, logic dictates that they must also be unchanged by T alone.
Meaning the laws of physics must work backward in time.
Mathematically, yes. The laws of science should work just as well if time is running backward.
But, and this is this huge glaring but, that brings us right back to the kitchen table. If I drop my coffee cup, the physics definitely doesn't look valid backward.
Yeah.
A cup reassembling itself is magic. It's impossible. So we have this massive contradiction. The deep microscopic laws of the universe are saying forward or backward, it's all good. But our actual lives, our macroscopic world is screaming, no, there is definitely a one-way street here.
That is the paradox. Why is there such a glaring difference between the past and the future in our everyday experience if the laws of motion don't actually mandate it? Why do we see the arrow if the atoms themselves don't?
And the answer, according to Hawking, lies in 3 specific arrows. He says we have to stop looking at single atoms and start looking at the bigger picture.
Right. Hawking identifies 3 distinct arrows of time. These are the phenomena that actually distinguish the past from the future for us. The first one, and the most fundamental one, is the thermodynamic arrow.
Which sounds incredibly fancy, but in the notes it seems to basically boil down to messiness.
It does. It's all about entropy. The second law of thermodynamics. It is arguably the most depressing law in all of physics.
Why?
Because it essentially says things fall apart. The second law states that in any closed system, entropy, which is a measure of disorder, always increases with time. It never, ever decreases.
This is the scientific version of Murphy's Law. If you leave a house alone, it gets dusty and falls into disrepair. It doesn't spontaneously clean itself.
Wow.
If you stop maintaining your car, it rusts.
Exactly. And think of the cup again. An intact cup sitting there on a table is a state of high order. All the molecules are arranged in a very specific structured shape. They're locked in a ceramic lattice. It's organized.
Right.
A broken cup on the floor is a disordered state. The pieces are scattered. The connections are severed. The thermodynamic arrow points in the direction of increasing disorder. We go from the cup on the table, which is ordered, to the shards on the floor, which are disordered.
But why? I get that it happens, but why can't we go the other way? Why doesn't nature let us have the self-assembling cup? Is there some kind of force that's pushing the shards apart? Is there an anti-assembly police force in the universe?
No, there's no force pushing them apart.
Yeah.
And it's not that nature strictly forbids it. It's not actually physically impossible for all those atoms to move in just the right way.
Wait, hold on. It's not impossible.
Theoretically, no. If you could somehow precisely control every single air molecule, every vibration in the floor, and every atom in the ceramic shards to push them all together at the exact right moment with the exact right energy, they would reassemble. The equations of physics allow for that possibility.
So why don't we ever see it?
Because it is statistically, unbelievably, mind-bogglingly unlikely. It's just a numbers game. It's all about probability.
Explain the probability here. How does unlikely become never happens in the real world?
Okay, think of a jigsaw puzzle in a box. Imagine it's a picture of the Mona Lisa, 1,000 pieces.
Okay.
There is one and only one arrangement of those 1,000 pieces that makes the complete picture. That is the ordered state.
Got it. One single state, the picture.
But how many arrangements are there where the pieces are just jumbled up and don't make a picture at all?
Trillions. More.
Way more than trillions. A number so vast, it's basically meaningless. A nearly infinite number of jumbled arrangements.
Yeah.
Those are the disordered states.
Right.
Now, if you start with the puzzle completed, highly ordered, and you shake the box, what happens?
The picture breaks. The pieces get all jumbled up.
Right. They move into a disordered state. Why? Not because the universe has some vendetta against the Mona Lisa, but simply because there are so many more disordered states than there are ordered ones. When you shake the box, you are randomly selecting a state for the pieces to be in. The odds of randomly shaking the pieces back into the perfect picture are so infinitesimally small that you could shake that box for the entire lifespan of the universe and it would never, ever happen.
That really puts the broken cup in perspective. For the cup to jump back together, it would be like shaking that puzzle box and accidentally getting the Mona Lisa.
Exactly. The thermodynamic arrow, the direction of time that we perceive, is simply the path from the unlikely states, the ordered ones, to the much more likely states, the disordered ones. It's not a rigid rule written in stone, it's a probability. But the probability is so overwhelming that it looks like an ironclad rule.
So time moves forward because there are simply more ways for the universe to be messy than for it to be tidy.
That's the essence of it, yes.
Okay, that makes sense for cups and puzzles. That's the first arrow. The thermodynamic arrow, things get messier. but that's about things. What about us? What about the fact that I can remember eating breakfast this morning, but I have no idea what I'm going to eat for breakfast next Tuesday?
And that brings us to the second arrow, the psychological arrow of time. This is the direction in which we feel time passing. It's the direction of our memory.
And Hawking argues these two arrows are actually linked, right? That it's not just some coincidence that they point the same way.
They are deeply, deeply linked. In fact, Hawking argues that the psychological arrow is determined by the thermodynamic arrow. Our subjective sense of time is completely locked to the increase of entropy in the universe.
How does that work? I mean, my brain doesn't feel like a steam engine or a pile of broken glass. How does disorder create memory?
This is one of the most brilliant parts of Hawking's entire argument, and it takes a minute to really wrap your head around. Since we don't know exactly how the brain works in fine biological detail, he uses a model. He compares the brain to a computer memory, or even simpler, an abacus.
An abacus. Okay, old school. I like it.
Very old school, but the physics is crystal clear. Think of a computer memory bit, or just a single bead on an abacus wire. It can be in one of two positions, right? Position 1 or position 2, left or right.
Got it. Binary. A 0 or a 1.
Right. Before you record a memory, that bit is in a disordered state. Maybe it's random. You don't know if it's a 1 or a 0. It's effectively a messy, jumbled puzzle piece.
Okay, so an empty memory is a disordered memory.
To record a memory, to remember, I had oatmeal for breakfast this morning, you have to set that bit to a specific state. You have to move the bead from the left to the right. You switch the transistor to 1. You are creating order in the memory system. You are defining the state.
So wait a second. If I'm creating order in my brain by remembering something, aren't I violating the second law? I thought disorder always had to increase. If I'm making my brain more ordered, isn't entropy going down?
And that's the catch. And it's the cosmic cost of doing business in the physical universe.
Yeah.
You are creating local order inside your brain.
Yeah.
But nothing comes for free. To move that bead on the abacus or to switch that transistor in the computer requires energy. You have to do work.
And when a computer does work.
It heats up. The cooling fan turns on. It has to dissipate heat into the environment.
And a heat is?
Disordered energy. Heat is just atoms and molecules jiggling around randomly. So here's the cosmic balance sheet. You gain a tiny, tiny bit of order in your memory, the memory of having oatmeal. But the cost of doing that is releasing a large amount of disordered heat into the universe.
And the disorder from that heat is greater than the order gained by the memory.
Always. It is always greater. The equation always, always balances in favor of entropy. The amount of disorder created in the universe by the act of recording a memory is always greater than the amount of order gained by the memory itself.
Whoa! So literally, the act of learning, the act of remembering is an entropy-generating process. We are burning the future to remember the past.
That's a poetic way to put it, but yes, that's physically what's happening. We remember things in the direction that entropy increases because the very mechanism of memory relies on the increase of entropy. That is why the psychological arrow and the thermodynamic arrow must point the same way. We are effectively biological machines that consume order and excrete disorder, and our perception of time just tracks that process.
That explains the stock market joke in the text.
Right. Hawking jokes that if this weren't true, if your computer could somehow remember the future, you could make an absolute killing on the stock market. But you can't, because the future hasn't happened yet in the thermodynamic sense. The entropy hasn't increased in that direction yet. You cannot have a memory of a state that is deeply disordered compared to your current state, because the process of memory itself requires moving from disorder to order locally at the cost of much greater global disorder.
It's so weird to think that every time I remember where I left my keys, I'm actively making the entire universe a slightly messier place.
It's the price of consciousness.
So we have the arrow of messiness, the thermodynamic one, and the arrow of memory, the psychological one, and they're locked together. But there is a third player in this game, the biggest player of all.
The cosmological arrow. This is the direction of time in which the universe is expanding rather than contracting.
We know the universe is expanding. The galaxies are all moving away from each other. But why does that matter for my coffee cup? Why do these three arrows, disorder, memory, and cosmic expansion, all have to point the same way?
That is the deep question. Why are we in a universe that started highly ordered and is now expanding into disorder?
Because if the universe had started as a chaotic mess...
If the universe started as a maximum entropy mess, a big jumble, disorder couldn't increase. It would just stay messy. And if disorder didn't increase, we wouldn't have a thermodynamic arrow.
And if we didn't have that, as we just learned, we wouldn't have a psychological arrow.
We wouldn't have memory. We wouldn't exist.
So for us to even be here talking about this, The universe had to start in a state of high order. We need an explanation for why the Big Bang wasn't just a big mess.
Exactly. And this leads us to one of Hawking's most famous and mind-bending contributions, the no-boundary condition.
This is a concept that is really hard to wrap your head around, so let's take it slow. What does no boundary actually mean in terms of the beginning of everything?
The best analogy is one Hawking used himself, the surface of the Earth,
Okay, I'm visualizing the Earth.
a globe.
If you start at the North Pole and you walk south, you eventually get to the equator, and then you keep going and you get to the South Pole. But is there an edge to the Earth's surface? Is there a point where the surface just stops and you fall off?
No, it's finite.
Right.
The Earth isn't infinite, but there's no boundary. It just curves back on itself.
Hawking applied this idea to the beginning of the universe, specifically in what's called imaginary time. Now, imaginary, here's a mathematical term. It's not make-believe. Think of it like a horizontal direction on a graph versus a vertical one. He proposed that space-time is finite in extent, but has no boundaries, no edges, no singularities where the math breaks down.
And what does that imply for the Big Bang?
It implies that the universe must have begun in a very, very smooth, very ordered state. Picture the North Pole again on the globe. It's a single point, it's smooth, it's uniform, there's no jagged edge there.
So the universe starts smooth, like a pristine sheet of ice, as smooth as it could possibly be. It couldn't have been perfectly 100% uniform because of quantum mechanics. The uncertainty principle says nothing can be perfectly still or perfectly uniform, but it was as smooth as possible.
So the no-boundary condition gives us a clean, ordered start.
It does, a smooth start. Then the universe undergoes inflation, this period of incredibly rapid expansion. And those tiny, tiny quantum fluctuations, the little ripples in the smoothness, they start to grow. They get stretched out across the cosmos.
And this is where gravity comes into play.
Yes. Gravity is an attractive force. It pulls things together. So if you have a region that is just slightly denser than the region next to it, gravity will pull more matter into that denser region. It starts to clump.
And those clumps eventually become
Galaxies, and then stars, and planets, and us.
So the universe evolves from a state of exceptional smoothness, which is high order, to a state of being lumpy and clustered, which is disorder.
Exactly. And this is crucial. The expansion of the universe is what allows this process to happen. If the universe didn't expand, everything would just immediately collapse back into a black hole. The expansion pulls the smooth universe apart, which gives gravity the time and space to create these local pockets of disorder, which we call stars and galaxies.
Which means the cosmological arrow, the expansion, sets the stage for the thermodynamic arrow, increasing disorder, which in turn drives the psychological arrow, our memory.
Precisely. They are a cascade. The expansion allows the initial order to degrade into disorder, which allows us to exist and have memories of it happening.
It's a beautiful, elegant picture. Everything aligns. But, and here comes the plot twist, what happens if the expansion stops?
This is where we get into the science fiction territory that Hawking loved to explore, and this is where he made his famous mistake.
Right. Most cosmologists today believe the universe will expand forever, or at least for a very, very long time. But there's a scenario where gravity could win. The expansion slows down, it stops, and the universe starts to contract, the so-called Big Crunch.
It's not expected for at least 10,000 million years, but it's a valid theoretical question to ask. If the universe starts getting smaller, does the cosmological arrow reverse itself?
And if the cosmological arrow reverses, if the universe starts shrinking, do the other arrows reverse too?
That's the multi-billion-dollar question. If the universe contracts, does entropy start to decrease? Do broken cups suddenly start coming back together? Do people start living backward, being born from the grave, getting younger and younger, and eventually unbeing born?
It sounds absolutely wild, but Hawking actually thought this was true for a while.
He did. He was seduced by the symmetry of it all. He thought the contracting phase would be the time reverse of the expanding phase. It's a very aesthetically pleasing idea, you know?
Yeah.
A nice palindrome of a universe. You start smooth, you get messy, then you get smooth again.
Imagine living in that world. You'd wake up, check the stock market, see the prices for tomorrow, and make a fortune. Although, wait a minute. If you're living backward, would you even care about money?
Well, you'd be unspending it, I suppose. It gets very, very confusing very quickly. You'd be regurgitating your food, you'd be unsaying your words. But yes, Hawking published papers suggesting this might be the case. But then he ran into some resistance from his own colleagues and students.
Specifically, Don Page and Raymond Laflamme.
Right. They crunched the numbers on the no-boundary condition much more rigorously, and they pointed out a flaw in Hawking's logic. They said, okay, The no-boundary condition implies the North Pole, the beginning, has to be smooth. But there is no mathematical reason at all why the South Pole, the end, has to be smooth too.
So the universe could start smooth and just end in a jagged, messy, disordered crunch.
Exactly. They found that disorder would continue to increase even as the universe contracts. The arrows do not reverse.
So even in a collapsing universe, the cup still breaks, you still get older, you still only remember the past.
Yes. The thermodynamic arrow is stubborn. It just keeps pointing toward more and more disorder, regardless of whether the universe is getting bigger or smaller.
And Hawking accepted this.
He did. And I think it's worth pausing here to highlight what he says about this in the source text, because it's so important. He compares it to Einstein calling the cosmological constant his biggest mistake.
Right.
Hawking says, and I'm paraphrasing a bit, what should you do when you find you have made a mistake like that? Some people never admit they are wrong. It seems to me much better and less confusing if you admit in print that you were wrong.
That is just class. To just admit, I followed the math, I got it wrong, my students and colleagues corrected me, and here's the truth.
It's how science is supposed to work. And to really drive the point home for everyone, he uses the analogy of a black hole to explain why he was wrong.
Right, because a black hole is basically a mini collapsing universe, a star collapsing in on itself.
Exactly. If the arrow of time were to reverse during collapse, then falling into a black hole would be a very strange trip. You might expect things to get more ordered. You might expect to know the future.
He jokes about playing roulette in a black hole.
Right, he says, you wouldn't get to play roulette knowing where the ball goes next. You would just turn into spaghetti.
Spaghettification, the lovely technical term.
The tidal forces are so strong they just stretch you out. But the point is, inside a black hole, which is a collapsing region of space-time disorder, is skyrocketing. It's not reversing. So if it doesn't reverse in a black hole, it won't reverse in the Big Crunch.
So we've established that the arrows don't flip. But that leaves us with one final, nagging question. The anthropic principle.
Yes, this is what answers the question, why are we here now?
Right, because if the universe is going to expand and then maybe contract, why are we living in the expansion bit? Why aren't we living in the contraction bit?
Well, first, we have to look at what the conditions of the contraction phase would be like. By the time the universe stops expanding, billions and billions of years from now, what will it look like?
Dark, cold, pretty empty.
Or perhaps very hot, eventually, as everything crushes together. But crucially, the stars will have burned out. The protons and neutrons may have even decayed. The universe will be in a state of almost maximum disorder, maximum entropy.
Okay, so it's basically a soup of chaos.
And remember what we said about life, about the psychological arrow. We need a difference in entropy to function. We need to be able to consume ordered energy, like food, and expel disordered energy, which is heat.
We need a gradient. We need a slide down, thermodynamically speaking.
Exactly. In the contracting phase, the universe is already at the bottom of the slide. It's already fully disordered. There is no ordered energy left to consume. There is no food in a thermodynamic sense. There's no potential.
So intelligent life is literally impossible in the contracting phase of the universe.
That is the argument. And this is what's called the weak anthropic principle. We observe the universe to be expanding because if it were contracting, we simply wouldn't be here to observe it. We can only exist in the phase where the arrows align, where the cosmological expansion is providing the conditions for the thermodynamic arrow to operate properly.
So it's not that the expansion causes the disorder directly, but the expansion represents the phase of the universe's history where things haven't gone totally to mush yet.
Correct. We are riding the wave of the Big Bang's initial order. We are essentially burning through the fuel tank of order that was filled up right at the beginning of time.
That makes me feel incredibly small, but also kind of special. We are living in the Goldilocks zone of time.
We are. We are in the era of interesting things. After the Big Bang, but before the heat death or the final collapse, we are in the sweet spot where cups can break, memories can form, and deep dives like this can be recorded.
Speaking of recording deep dives,
Yeah.
as we wrap up, I think we need to address the cost of this discussion. We touched on it with the computer memory idea, but the source text has a very specific and kind of amazing calculation for the listener that I think we should walk through.
Oh, yes. This is a final takeaway, and it's a bit of a guilt trip from Professor Hawking.
So if you're listening, you've been with us for a while now. You've absorbed a lot of information. You've learned about C, P, T symmetry, the no boundary condition, the 3 arrows of time.
Let's just say, for the sake of argument, that you've recorded about 2 million pieces of information in your brain during this conversation. That's 2 million units of order. You have structured your neurons in a new way. You are hopefully a little smarter now than when you started.
Congratulations, that feels good, right?
Uh,
Gaining order.
but remember the cosmic bill. While you were listening, your body was running its metabolism. You were pumping blood, firing neurons, keeping your body warm. You converted about 1,000 calories of ordered energy, that bagel you ate or that coffee you drank, into disordered heat.
You sweated a little, you radiated heat into the room.
And the balance sheet, how does it look?
Hawking actually ran the numbers. The disorder you created in the universe by listening to this is about 20 million units of entropy.
Wait, run that number by me again.
20 million. That is the increase in messiness that you personally caused.
And I only gained 2 million units of smarts.
Correct. The disorder you created is about 10 million times greater than the order you gained in your brain.
So, by listening to this deep dive, by trying to understand the universe and bring order to our own minds, our listeners have actively made the universe a much, much messier place.
It's the ultimate irony of existence. In our quest to order our minds, we dramatically accelerate the disorder of the cosmos. Well, on that slightly depressing note, maybe we should stop talking. I think we've done enough damage for one day.
I think so.
Yeah.
Stop ordering your brain now, folks. Go save the universe a little entropy.
Go brick a cup. It's going to happen anyway. Thanks for listening to The Deep Dive.
See you in the future. Or what's left of it.